Alright, so this lecture is going to be discussing creating geospatial data. There are many reasons why you might want to create your own geospatial data. The main reason is that data you need has not been created by anyone else. Even though GIS and digital data have been around for a long time, there is still a large need for the creation of new data covering many different facets of our world at many different scales. A couple of additional reasons that you may want to create geospatial data are that the data you need is on a paper map and it needs to be converted to digital format so it can be used in your GIS software. And the data available may be a different scale than you need. For example, let's say you want to show a map of where all the state parks are in Virginia. However, all of the park datasets are extremely detailed and look very poor at a statewide scale because of the intricate detail of the park boundaries. In this case, you would need to create a new park dataset suitable for displaying at a smaller scale, or simplify the existing dataset so that it can display better at the smaller scale. Another reason to create new geospatial data is the possibility that the data available is too old for your purposes and you need an updated version of the data. There are many other reasons why you would want to create geospatial data, but these are the most common reasons that you should be aware of. So there are two types of data sources that you can derive digital geospatial data from: hard copy and digital. Each of these data sources has their own positive and negative aspects as the way to store data. Let's look at these aspects, starting with hard copy data. Hard copy data, such as data stored on paper maps, was the most common medium of storage for GIS until the 1980s. The positive aspects of hard copy storage is that it is a stable medium, which means that it cannot get a virus, can't run out of battery power, or it can't crash like a computer. Hard copy data is also cheap to produce and is easily portable, and it does not require any specialized hardware or software for use. This provides a very low barrier for use, and it makes a paper map easy to use and understand by a very wide range of users. Hard copy data is semi-permanent so long as it is properly stored. The negative aspects of hard copy data are that it's not reusable because it cannot be easily updated. A hard copy map, for instance, is a static representation and it can only be updated by printing over the existing map, which is often not desirable. Digital data has become a common storage medium for GIS data since the 1980s as computers became more widely used and storage capacities grew larger and prices dropped significantly. The positive aspects of digital data are that it is stable so long as it is properly maintained, backed up, and occasionally transferred to a modern storage medium. And then digital storage is now extremely cheap and can store massive amounts of information in a very small space. Digital data is semi-permanent. What is meant by that is that the data structures must be set up to allow for archiving of historical values of information. However, this is often not the case. Therefore, previous data is often overridden when values are updated, and there is no way to see the previous version or value. Digital data is extremely flexible. Digital data can easily be updated, and it can be used for many different purposes. Negative aspects of digital data are that it is not portable without specialized hardware and software. This significantly raises the barrier of entry for users, and the hardware and software may not be easily understood by the users either. Additionally, the data may be tied to specific systems that may depreciate over time, so there is a need to continuously update the data into newer hardware and software systems. Alright, so next we're going to talk about coordinate transformations, which are also known as registration. Coordinate transformation is the process used to bring spatial data into an Earth-based map coordinate system using a series of control points. For instance, imagine you are in an airplane and you took a bird's eye view of Earth. You could copy that picture from the camera to the computer and attempt to place it in your GIS software. What would happen is that the image will not show up in the right place on Earth, but it will instead most likely be placed at the intersection of the equator and the prime meridian. This is because the aerial photo you took is not referenced to any location on Earth. In fact, the picture has its own arbitrary coordinate system, which starts from 0, 0, typically the lower lifting corner, and it increases in positive direction along the x and y axes. This is why, when you add a picture into a map, it places it at the intersection of the equator and the prime meridian, because that is the 0, 0 point in the latitude and longitude system. In order to make the aerial photo show up in the right position on Earth, we must perform a coordinate transformation. The idea is that you identify locations that are in your picture on the ground and get the coordinates for those locations. You then match up the known coordinates of the positions on the ground with where it is located on your picture. Once you've chosen enough control points, the computer's software can perform a transformation by placing the picture where it belongs on Earth. During the transformation, the picture is often stretched, rotated, and deformed to match the location of the control points on the Earth and on the photo. So in order to perform the coordinate transformation, you must use considerable care when choosing which control points to use. The control points are used to transform the data from the source coordinate system to the map coordinate system. The source or digitizer coordinate system is the case for our in the case for our example is the coordinate system used in the digital camera. The map coordinate system is the coordinate system that you wish the transfer to, such as the state plane coordinate system or latitude and longitude. Therefore, in order to perform the coordinate transformation, we need to identify control points. One set of control points from the source or digitizer, and one set of control points from the map. When choosing control points on both the source and map, you should choose control points that have the highest feasible coordinate accuracy. This means that if you're looking for an accuracy of 1 foot, your control point should be no larger than 1 square foot in size. Additionally, for the control point, the accuracy of the control point's location should be at least as good as desired overall positional accuracy. That means if you want centimeter level accuracy, then you should not measure the location of your control point to the nearest 5 meters. And lastly, your control points should be evenly distributed throughout the area. By distributing the control points evenly through the area, you are providing sufficient coverage to provide a good transformation across the entire area. This in contrast to only choosing control points in one corner of the dataset, which in that case, only the corner of the dataset will be accurate, and the rest of the dataset will contain significant amounts of error. So there are two common sources of control points. The first source is a land survey performed by a licensed land surveyor. Land surveyors are experts at measurement and can provide very accurate and precise control points based on existing or new benchmarks that are placed around the nation. The second data source is an existing map that covers the same location as the source data set. If the existing map is already registered, then you can pick the coordinates from the map as your control points. When choosing control points off of an existing map, good choices are permanent features that are easy to see from the air, such as concrete corners, bases of buildings, or aerial photo targets, which are those white crosses you often see painted on the highway. Poor choices will be items that move or are difficult to see from the air, such as cars, trees, or street paint. Alright, so now let's talk about digitizing. Digitizing is the process of converting coordinates of features from a data source, such as a paper map, into digital format. Digitizing can be thought of as tracing an object. The general idea is that we will use an input data source, such as an aerial photograph rectified to the Earth-based coordinates, and then use an input device to trace and record the features from the map as a vector feature. There are two methods of digitizing: manual digitizing and automatic digitizing. Manual digitizing is when a person digitizes the features from the source data manually. This process is often time-consuming, tedious, and prone to human error. However, It allows the human to intelligently determine where to digitize and what to digitize. The second method of digitizing, automatic digitizing, is where a computer program is trained to identify features on the input data source, and then automatically traces those features. Automatic digitizing can save a significant amount of time. However, the features need to be easily identifiable on the input data source. Training the software to identify the features may take quite a bit of time, and a human may still need to clean up errors in the automatic digitizing results. When an object is digitized from the computer into the computer from the source dataset, it is composed of two parts, a node and a vertex. A node is a start or end point of a line segment or a point. A vertex is an intermediate point of a segment and must exist between two nodes. As an example, if we look at the digitized object on the side, we can see that there are 4 nodes and 5 vertices. As we know that nodes determine the end and beginning of a segment, and vertices are continuations of the same line segment, we can identify 4 separate digitized line segments in this figure. Starting at the bottom, we have a node, followed by 4 vertices that terminates at the base of the triangle. That is one line segment. The second line segment is between the 2 nodes on the small leg of the triangle. The third line segment are the 2 nodes on the short leg of the triangle and go through the vertex at the other end of the triangle. The fourth and final segment is the short line that offshoots from the top of the triangle to the end of the short line. When digitizing manually, there are 2 common digitizing errors. The first common digitizing error is known as an overshoot. An overshoot is where lines cross over existing lines and nodes where they should have actually connected. For instance, imagine if we are digitizing pipelines off of a map and we have 2 pipes that connect in a T intersection. However, when digitizing, the pipe that is forming the stem of the T does not connect exactly with the other pipeline. Instead, it passes over and through it in the digital data, making it cross instead. This is an example of an overshoot. An undershoot is when nodes do not quite reach the intended line or node. Going back to the pipeline example, if the 2 pipelines do not intersect because the second pipeline was terminated just short of where the pipeline was supposed to connect, this would be considered an undershoot. When performing digitizing, you should follow these 5 steps. Step 1. Create or use an existing data set to store the digitized data. You should select the geometry type of the dataset. Step 2. Load the source data into the GIS program. Step 3. Register the source to Earth-based coordinates if it is not already. Step 4. Manually or automatically digitize the features into the digital dataset. And step 5 is to save the newly digitized features. You always have to save, especially in ArcMap. If you just move on to the next thing and you don't save your edits, it's gonna disappear and you'll be very frustrated. Alright, so this section defines manual digitizing in more detail, and it shows an example of a manual digitizing task. Manual digitizing is the human-guided capture of features from a map, image, or source. There are 2 methods of manual digitizing: on-screen digitizing and hard copy digitizing. On-screen digitizing is probably the most common form of digitizing today, and it is where a source is scanned or downloaded into the computer's memory and loaded into digitizing software. The mouse and keyboard are used to digitize features, while the source feed on the screen. Hard copy digitizing is where the original source is taped to a digitizing table, which is connected to a computer. The digitizing puck, which is similar to a mouse, is used to digitize features from the hard copy source into the computer. The purpose of the digitizing puck is to feed coordinates into the computer based on its location on the digitizing table, which would be the source's coordinate system. Alright, so this video is going to show an example of on-screen manual digitizing. All right, so first you'll need to create a file to digitize into. Make sure to select the correct geometry and set the spatial reference. Before you digitize, you will need some reference data. Here we're using an ortho photograph. Here, we are changing the symbology to make it easier to digitize. Now, we will edit the attribute table to include a name field. We are now naming the field, providing an alias, and setting a data type. Now, we are ready to draw. Or better put, create geospatial data. Now, we can edit the attribute table. Finally, we save our edits. And then lastly, we can calculate area. Well, we don't need to go into all that. But that kind of shows you how to do manual digitization. All right, so now let's talk about automatic digitizing. As this course does not include a lab for automatic digitizing, a case study will be discussed. Automatic digitizing is the computer-guided capture from a map image or source. This is different from manual digitizing, where it is a human-guided capture. The way in which the computer performs automatic digitizing is that it uses algorithms to identify and digitize the features. While these algorithms are often quite powerful, it often requires an initial training period that may take time. Some of the algorithms available in automatic digitizing software can learn how to identify the features and is supposed to trace based on full color scans instead of requiring an initial binary classification, as you will see in step 1. So let us now walk through an example of automatically digitizing contour lines from a contour map. What you are seeing on the slide is actually 3 contour maps that have been mosaicked or pasted together. As you can see, there are quite a few red contour lines on this map, which would take quite a long time for someone to manually digitize. In an effort to save time, we will automatically digitize the contoured lines from this map. This map is a good candidate for automatic digitizing because the contoured lines are drawn in a strongly contrasting red, and no other features on the map are the color red. This helps the computer easily identify and isolate the contour lines of the map. In order to assist the computer in isolating the contour lines, the digitized contour map has been classified into a binary image. Wherever there was red on the map is now black, and where the color red did not exist on the original map, it is now white. This initial step in the automatic digitizing process and is critical for ensuring that the computer can easily distinguish features from the map. It is important to note that other digitizing software does not need the user to isolate the feature for it, as it can work with selected colors. The second step of automatic digitizing is to run the automatic digitizing algorithm. The red lines now shown on the map are the actual digitized vector lines. We cannot see the original raster representations of the contour lines, as they are underneath the digitized lines. This means that the automatic digitizing algorithm did a good job of tracing the contour lines. The third step in automatic digitizing is to clean the results of step 2. On this particular map, if the contour lines make sharp turns, the contour lines become disconnected. For instance, the blue contour line should connect with the red contour line. Excuse me. It should connect to the red contour line that it touches towards the center of the screen. However, as this is a significant change of angle, the automatic digitizer considered this to be separate contour lines. Therefore, it is up to the user to either modify digitizing parameters so this may be caught and run step 2 again, or to manually connect the contour lines themselves. This is what the corrected contour lines look like. In this case, the user opted to manually connect the contour lines. Now that the error has been corrected, the user would continue to review the automatic digitizing results to find the other errors and correct those. The fourth step is to assign the contour lines values into the attribute table of the newly digitized contour lines. In this case, a tool was downloaded that makes it easy to assign multiple contour lines at once by drawing a line across multiple contour lines and then specifying the first contour line it crosses contour value and how much it should increment each additional contour line that passes over. So in this case, the contour line at the bottom would be assigned a value of 2000, the line above it 2100, the line above that 2200, and then 2300 respectively, and finally 2400 as the last top contour line is crossed. This is the result of the automatically digitized contour lines with the contour values labeled. Finally, this shows the complete digitized contour lines overlaid on top of the original contour map. As you can see, the digitized contour lines follow the original contour lines extremely close, and it does a good job of saving the manual digitizer time. Now that we've seen both automatic and manual digitizing methods, let us take a moment to discuss positive and negative aspects of the two methods. Manual digitizing is typically sufficiently accurate as humans can interpret maps easier than computers. As digitizing is not typically a job that requires highly skilled operators, the training period is often short and the labor is cheap. The negative aspects of manual digitizing is that the map scale impacts the accuracy. Different operators may work better or worse at different scales, as some maps may have such fine detail that the operator has a hard time accurately digitizing the intended feature. The hardware that the operators are using may also impact accuracy, if the operators are not provided with capable hardware and software. Finally, different operators will digitize at different qualities and may interpret what is being digitized differently. This may lead to inconsistent digitizing results. Now let's focus on automatic digitizing. Automatic digitizing is good for large projects that would take a large amount of staff and time to complete. There's no initial operator error, but the results will require manual editing, as we just saw. Automatic digitizing can work well with a large number of elements on a map, so long as those elements are easily distinguishable by the computer. Negative aspects of automatic digitizing is that the software can be very expensive. However, if the project is sufficiently large, the expensive software may ultimately be cheaper than the labor that would be required for manual digitizing. Automatic digitizing can also only translate and trace, but cannot interpret what is actually looking at. Automatic digitizing may be more susceptible to misdigitizing areas in the map where the scanner messed up or had a smudge. For most of your digitizing work, if it is sufficiently small in scope, manual digitizing will be the preferred method. However, if the digitizing work covers an extremely large area and the source has easily distinguishable features, automatic digitizing can provide a large amount of time and money savings. All right, so now let's talk about feature generalization. We should first step back and remind ourselves that maps are simply abstractions of reality, or our conceptualization of the world around us. That is, they are someone's viewpoint of how the world is organized. While we would like to store infinite detail about reality in geospatial datasets, it's simply not possible, and it's not always desirable. Constraints on an infinite representation are the size of the map medium, insufficient resolution of sensors, finite disk space, scale at which we are representing reality, and so on and so forth. Additionally, you may not need to represent all aspects of reality for your mapping purposes. Our inability to store infinite detail of reality and geospatial datasets means that we must generalize the features that we are storing. Feature generalization is the approximation and simplification of real features represented on a map. The main purpose of feature generalization is to aid in map legibility by reducing the complexity of features being shown. What is most important to remember about all feature generalization is that a properly generalized feature should still maintain the same character of the original objects. That means, for example, if we reduce the number of curves in a stream, we should still be able to identify that feature as a simplified version of that stream. In order to discuss the four methods of feature generalization, let us first see what the source data was. Source data for this digitizing project was a digital orthophoto quadrangle quad. Houses could be easily identified on those photos, and the user wanted to digitize the footprints of the houses and roads. The original source data is shown on the left with the digitized house footprints laid on top. On the right, we see the digitized data without the source imagery behind. We will now focus on only the digitized objects and ways in which we can generalize those objects to aid in map legibility when we display this information on maps. For reference, the original digitized data is in the top left corner, and the top right corner is the first feature generalization method. The process of fusing is to combine the geometry of adjacent features that are close together. In this example, we have fused together 8 houses so that the fused data now only has 9 building structures, instead of the original 13. As you can imagine, if we zoom out of the fused data, we will still be able to understand the characteristics of those houses around the street intersection. The second method to discuss is simplification, which is in the lower left corner. To simplify features, you remove vertices where the features show a reasonable amount of complexity. For instance, looking at the house south of the intersection, we see a sort of stair-step pattern in its construction. If we remove the stair steps and square off that corner, we still maintain the character of that house, as the relative location and shape are still intact. And the lower right-hand corner is the displaced method. Here, the houses are moved closer to the streets. The houses could have also been moved further away from the streets. In either case, what is important is that the relative positioning of all features involved still be maintained. In the upper right-hand corner is the omitted feature generalization method. Here, features are simply removed from the dataset. You may want to do this for lakes, for instance, where a large lake is surrounded by multiple small, insignificant lakes. If we remove the small, insignificant lakes and keep the large lake and zoom out, the map reader can still understand that there is a water body in that location. Last, in the lower left corner, is exaggeration. This is perhaps the most common method of feature generalization. For instance, on a road map for a state, the roads are greatly exaggerated so that they can be seen on the map. If the roads were drawn to scale, they'd probably be so thin that the printer could not print the map, or that the reader couldn't even read the thin line. Therefore, by exaggerating the road, the original characteristic of the road is still maintained, and a map reader can easily see the road features of importance on the map. Now you're Now you're familiar with methods for feature generalization. We should discuss some broad directives for feature generalization. First, you need to observe the map purpose at all times. Do not include pointless details or features, and vice versa. Additionally, the degree of simplification must be related to the purpose. For instance, if you are creating a map of a river for a kayaking club, you would not want to overly simplify the river, as all of the intricate bends and features of the river are what the kayakers really want to see. Next, the scale that the map is being produced at should have a bearing on the need for simplification. If at the current map scale you can easily see all the features on the map, then there is no need for feature generalization. Again, you should maintain the essential character of the feature and area. Even if the features have been fused, simplified, displaced, omitted, or exaggerated, the map reader should still identify those features. And lastly, be consistent in your treatment. If you omit a large number of one type of feature layers on a map, but you do not omit any other type of feature layer on the map, the user may assume that the map layer with all of the omitted features is just as accurate as the detailed layer. All right, well, that concludes today's lecture. All right, if you have any questions on creating geospatial data, again, feel free to ask me in class, email me, or if you're watching this just on YouTube, feel free to post comments there. And if I see them, I will definitely respond to them. All right, have a great one.